We just stated the D-separation theorem for conditional independence in directed graphical models, and in this video, let's take a look at an example. Let's work out an example, actually a few examples. So let's write down a graph. Let's write down a little graph, and we'll see what we can determine using the D-separation theorem. So I picked a graph that would be nice for this. So let's draw this little graph. It's going to have a sort of X shape here, and then we're going to go down, have a few other vertices downstream, something like this. And let's number these vertices. So we'll have, this will be 1, 2, 3, 4. We'll keep it ordered. I'll make this 5 to keep it ordered. 6, 7, 8, so that lower numbers always precede higher numbers. So this is a nice little graph. And let's condition on something. So let's condition on 3. So I picked, let's say that C. So we're conditioning, remember above here. C was the thing that we're going to be thinking about conditioning on. And so we're going to think about sets A and B that are D-separated by C, or we'll see if they are D-separated by C. So C here will be just this vertex number 3. And we'll sort of associate, we'll associate some random variables. So I'm associating some random variables, x1 up to x8, with each of these vertices. And let's go ahead and draw that fact that that's going to be conditioned on. So I will, following the convention of shading the thing that we're conditioning on, we'll shade number 3. All right, so now let's see. So now, what do we want to know? We want to know for pairs. So let's think about, just to keep things simple, let's just think about pairs of individual random variables. And we want to know things like, is xi conditionally independent of xj given c? And in this case, c is x3. So the D-separation theorem, let's remind ourselves what the D-separation theorem says. D-separation says, if A and B are D-separated by C, then they are conditionally independent, given C. So here, if we had two vertices, like let's take 1 and 4. So if I is 1 and j is 4, so let's go ahead and put that. Let's go ahead and put I. Let's make maybe we'll make a little table here. So we'll have I and j, and we'll determine whether I and j are D-separated. So if I and j are 1 and 4, then to know if xi and xj are conditionally independent given x3, then if we can determine if they're D-separated, then we can say yes. If we determine that they're not D-separated, then we don't know. So let's see, how do we determine if they're D-separated? Well, what is D-separation? D-separation is A and B are D-separated if all paths from a vertex of A, in this case it would just be, say 1, to a vertex of B, so that would just be all paths from 1 to 4, if all paths from 1 to 4 are blocked with respect to C. So all paths from one of these vertices, from I to J, is blocked by C. So what does it mean for something to be blocked? Let's write down here what it means. What does it mean? Remember we can remind ourselves here. This was the definition of blocked. A path between two vertices is blocked with respect to C if it passes through a vertex V such that either A, the arrows are head to tail, or tail to tail, and V is in that. So let's make a first condition down here. So the first possibility for something to be blocked, so let's make a little table of rules. So we'll have some rules. So rules. We have something like this. This is a head-to-tail relationship. Or we have a tail-to-tail relationship. something like this along our path, then this is blocked if that vertex, let me say it this way, I'll just draw it sort of visually, it's blocked if that vertex is being conditioned on. So it's blocked if that vertex is being conditioned on. Let me make that a little darker maybe. And if it's not conditioned on, then it's not blocked. On the other hand, maybe use a different color. So if we have a head-to-head relationship along the path, then this is blocked. It's blocked at that vertex if that vertex, so what was B? So that was A. This was condition A, and this will be for B. So maybe I'll write this. So this would be case A, and this would be case B. And for B, what was the criterion for a path to be blocked? It was blocked if it passes through a vertex V, such that, in the case of B, the arrows are head-to-head, the vertex is not in C, and none of its descendants are in C. So for this one, blocked if, let's say, no, so not, well, maybe I'll label it V. V not in C, and no descendants in C. So in our case, this is saying it's blocked if V is not equal to x3, V is not equal to 3, rather, and none of its descendants are equal to 3. So these are our rules. These are our two sort of rules that we will use to determine if two vertices are d-separated. Okay, so let's think about 1 and 4. So let's start with just a nice simple one, 1 and 4. Actually, let me move this over a little bit so we have room, because we're going to make a list of these. Okay, so for 1 and 4 is the path. So all the paths are all the paths from 1 to 4 blocked. That's what we need to determine in order to determine if this is d-separated. So there's only one path from 1 to 4, right? It's 1, 3, 4. Maybe I'll put that. So 1, 3, 4. And is it d-separated? Well, there's only one vertex on the path. It's 3. And does it satisfy one of? So is it blocked? Does it satisfy A or B? Well, it's a head-to-tail relationship, so it looks like this one. And it's conditioned on, so it's blocked. So this is blocked, so this is d-separated. So yes, it is d-separated. And so we can determine that x1 and x4 are conditionally independent given x3. Let's think about 1 and 2. So are 1 and 2 d-separated given C? So here, remember C, so we're always conditioning on 3 here. This is our set C. So 1 and 2, again, so since this is a tree, there's always going to be a unique path between any two vertices. So we only need to consider one path. That makes this a nice simple sort of graph to work with. So 1 and 2, we go 1, 2, 3, 2. This is a head-to-head relationship. So is B satisfied? It's blocked if V is not in C and no descendants are in C, but 3 is in C. So it's not blocked. So no, not blocked. So we cannot determine, it's undetermined whether 1 and 2 are conditionally independent given 3. So we cannot say that they're necessarily dependent, nor can we say that they're not. Let's think about another one now. Let's think about 4 and 5. So 4 and 5, there's again a unique path here. So 4, 6, 5, is this path blocked or not? Well, we have a head-to-head relationship here. So that would be case B. And it would be blocked if V is not in C and no descendants are in C. Well, 6, so 6 is V in this case. 6 is not in C, and it has no descendants in C, right? So that is blocked. So you're starting to see a pattern now, and let's write down, let's annotate this graph in a way that will make this a little bit easier. So whenever we have this sort of situation, there's always a tail involved, right? And it's blocked if that vertex is being conditioned on. So let's do this. So whenever we have something which is conditioned on, let's go ahead. We know that we're never going to go through this tail, right? Because it's blocked. Any path that goes through that tail is one of these things. And the same for this tail. So let's annotate these with these red dots. So that's like a stop sign. So you can't go through there. And let's think about case B. Let's annotate it to denote case B. So case B is, if it's a head-to-head relationship, it's blocked if the vertex is not in C and no descendants to C. So let's look wherever we have head-to-head relationships, and let's see. Let's annotate the ones. Let's block the head-to-head paths that are fall in this situation. So this one, 3 is in C, so we don't need to indicate that. But 6 is not in C and it has no descendants in C. 6 is not in C and has no descendants in C. So let's make a little, maybe we'll put a little dot between these two guys here. Something like this, a little red stop sign. So you can't go from, through 5, 6 to 4 or 4, 6 to 5. So now we can just very quickly read off these properties, right? 1 to 4, boom, blocked. Goes through that stop sign. 1 to 2, not blocked. There's no red stop sign. 4 to 5, blocked. It goes through this stop sign. Let's think about another one. 4 to 7. Or 7, there's 7. 4 to 7 is not blocked because it does not pass through. This is only a stop sign between these two heads here. So this is a no. So they are not deseparated because the path, there is only one path, and so every path, so there was a path, right? In order for to be deseparated, every path would have to be blocked. And we had a path here, 4, 6, 7, that was not blocked, so it is not deseparated. Let's do a couple more. 4, 8. 4, 8 is clearly deseparated. How about 4, 6? They're squeezing these together here. 4 and 6. 4, 6 is not blocked, so that's not deseparated. What about 2 and 7? 2, well, if clearly going to be blocked here, it'd have to go through this stop sign. So 2, 7 is deseparated. Do a couple more. 2, 5. 2 to 5, clearly blocked. It'd have to go through both of these. It would have to go through this one and this one, right? It would have to go through this one because it was going 4, 6, 5. So that is deseparated. And let's do one more. Let's do 5, 8. 5, 8. 5, 8. That would have to go through this stop sign and these. So that's clearly blocked also. So that's a yes. So that was amazing, right? We were able to just immediately read off these conditional independence properties from the graph.